Hello, my name is Subhash Basu. I'm going to talk to you about a new technique for fault simulation which is disrupting the world of fault simulation. The utilization of AI ML is the core fundamental, and I just wanted to explain that fault simulation initially it's a very difficult task in the sense that every node in a circuit has to be toggled at stuck at 0 and stuck at 1. What we are proposing here is we are proposing a next generation regenerative AI approach for fault detection, enhanced designs, accuracy and speed. The title itself might sound a little difficult or complex, but actually, as I explain further, you will find that it is extremely simple techniques. So moving on to, as I was explaining about the fault simulation issues, which has got traditional stack at 0, stack at 1, and through typical IP, which may be 500,000 gates. It could also be SoC with more than 20 to 80 million, maybe even higher number of gates. So obviously something which is requiring this kind of simulation would require a very, very high compute, at least 3x what a normal simulation would be. So how do I apply my AI ML model? No brainer. A very typical data science engineer will tell you that there are certain steps which you apply, but what you are doing over here is you're running a regular simulation with the stuck at 0 and stuck at 1 fault in each and every input port as well as every internal node you want to check on. What you're getting is a very voluminous test vector output file, which you will then convert it into a CSV file format and send it into our AI engine. Now the AI engine is going to look at 80% of your test vectors and is going to build up a model using the regular hyperparameters and of course the TensorFlow Keras API, neural networks. It's going to build up a model which you can then test on the balance 20%. And once you're done, you have a very robust model. So in the next round, this is the important thing, in the next round you don't need to run the 80 or 100% of your test vectors. You need to only run 20% of your test vector, and the model will generate you the outputted expected outputs. And when you do that, you can then compare with the golden test case and which the model which you have been developing had, and with the next run cases, and you'll be able to predict exactly where the faults are. As we get into the summary, we are going to look at what the advantages are. Obviously, the biggest advantage is time. We need 20% vectors to do the simulation here. Secondly is the compute. I don't need high performance computing any longer because now I can do it on an AI engine. There are other advantages as well as certain disadvantages, but overall what we have found, as you will see as we move forward, that there is a huge return on cost, time, which means time to market guidelines, and the adoption of technology will ensure that we have far more well-tested ASICs and a safer environment. Thank you very much.